So the entire unit has been on understanding the characteristics of a function by analyzing its derivatives. First day, we found critical points. That's when we have a horizontal tangent or a tangent that's undefined. Day 2, we then saw if those locations of those critical points are maxes and mins. We discovered that by analyzing f prime from left to right. If it was positive, we know f is increasing from left to right. If f prime is negative, we can see that f is decreasing from left to right. Day 3, today, we will analyze the second derivative to examine the concavity of a function. Okay? So that's Unit 4, Lecture 3. It is analyzing f double prime to examine the concavity of f. And Day 4, which will be on Monday, we will put it all together, and we'll talk about speed and more of your position, velocity, acceleration graphs. And it's all related. So Unit 4, Lecture 3. Analyzing, you probably don't have to write it like that. It's analyzing f double prime to examine the concavity of f. Okay, and we'll start off by just seeing if you guys understand what something or the graph of something that is concave up looks like. I think you maybe talked about it in chemistry a little bit, definitely in physics, maybe you talked about concavity. So what does concave up look like? Anybody? Draw it with your finger. Anybody? Mr. Rogers? Like that, right? Concave up looks like this. If you're concave up, you open upwards. You could have a graph like that. That's simple, right? If you are concave down, you would then open downwards. You'd look like this. Okay? And this entire graph is concave up. This entire graph is concave down. We will see that graphs are not always all one way or the other. You can have portions of graphs that are concave up and portions of graphs that are concave down. An example could be like this. This part here, so here, this is concave up. This piece here, until we get here, that's concave down. This entire piece here opens upward, then we open down, then we open back up. So all sorts of concavity going on in a function like that. Well, after today, we'll be able to understand, given a function, when we are concave up and down by analyzing the second derivative. Okay, we'll come back to this example. So let's look at something that is concave up, something like x squared minus 2 or something. This function is concave up. I want you to go ahead and sketch the first derivative and then sketch the second derivative of that. Now remember how we do this. We're going the way that we've learned already and that we've practiced, that we're comfortable with. Kind of pick some x values, then analyze the slopes of your tangents, and then you're going to plot those tangent slopes. On the graph of f prime. And then you'll do the same thing to plot the graph of f double prime. So I can see my tangent is negative here, then it is a little less negative, then it's 0, then it's positive, then it's definitely more positive. So I got a negative, a less negative, a 0, a positive, and a more positive. giving me something that looks like a line. Now, after last class, you should be able to go from here back to the left, whereas that wasn't something you could have done until last class. Okay, but now we know that this means my function is decreasing, it then will hit a minimum, and then it'll be increasing. But that was last class. We're moving on. So now we sketch the second derivative. Well, same thing. At these points, we find the tangent slopes. They are positive and consistent. They don't have to be consistent, but we all know that they're positive. They could be, you know, more or less positive in certain locations, but for this situation, we are looking at a positive line for my second derivative. So what do you think we can deduce? If my function is concave up, my second derivative is what? Positive. That is our first test for concavity. If f double prime of x is positive, then f is concave up on that interval. You could probably assume what's going to happen when f is concave down, but let's go ahead and sketch just to make sure. This is concave down. Go ahead and sketch f prime and sketch f double prime. So just pick some x-coordinates, plot the slopes. We'll find the slopes and plot them on the graph of f prime, and then do the same for f double prime. We should get positive, less positive, 0, negative, more negative, giving us graph of f prime here. And then we take the derivatives of this. We got negatives, 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 negatives. Graph of f double prime, given that the graph of f is concave down, is all negative. There's your second guy. If f double prime is negative, then f is concave down. On that interval. Well, what if f double prime was 0? Exactly. We would not have any concavity at all. Something that would not open upwards or downwards would be like a line. If you think about a line, the first derivative of this line here, this is f, first derivative would be a positive line, right? All in positive, but then the second derivative, the slopes of this horizontal line would all be 0. So f prime is 0, we have just like a line. Well, that's if everywhere is 0. There are situations where we'll just have f double prime equal to 0 at just a point. Okay, so if it's a line, if we're talking about an interval, But if f double prime is 0 at a point, let's examine what we would have, what type of situation that would be. So let's look at this third graph. Is this concave up or concave down? Both, right? This piece is concave down, this piece is concave up. We'll go ahead and sketch f prime and f double prime. So we got positive, less positive, 0, less positive, more positive, positive, less positive, 0, positive, more positive, and then we'd have negative, negative, 0, positive, positive, positive. Well, where is our graph concave down? Maybe just by looking at the function on the left. Yeah, over here, right? So over here, we are concave down. Well, look, f double prime, when x is less than 0, is negative. We can kind of set up a number line to kind of show that. We can say the sign of f double prime, so the values of f double prime to the left of 0 are negative. Well, we can see from our graph that this is the piece where we are concave up, we are opening upwards. Well, the sign of f double prime is positive here. Notice right at 0, we have a point when f double prime equals 0. That's a point where we don't have concavity. It's a point where we change concavity from being concave down to being concave up. We call this point a point of inflection. Okay? Points of inflection occur or you could say they possibly occur when f double prime equals 0 or they're undefined, and when f double prime changes sign. You could change sign from positive to negative or negative to positive. Okay, so if we look back at that previous graph when I'm talking about this big guy, we know we are, for the function f, we are concave up here, we're concave down here. This entire piece we're concave up. This is where we're concave down. This is where we're back to being concave up. Well, this point here, where I kind of drew like a little line separating things, these are points of inflection. And you can just use POI for short if you want to. Well, kind of seeing what we did here, when we had this one point of inflection and we drew this number line, we're going to do the same thing almost as what we were doing with f prime to examine concavity. What I'm going to do when I'm given a function is I'm going to be able to draw a number line and examine the signs of f double prime. And let's just assume this is at like 1, 2, 3, and 4. Here, the sign of f double prime, since we are concave up, would be positive. Here, the sign of f double prime would be negative, and it would be positive from 2 to 3, negative, then positive. This is telling me where we are concave up. This is showing me where we change signs and that we have points of inflection at all these locations. So if I ask you a question, determine the intervals for which the following functions are concave up or concave down and specify the inflection points, you're going to think, and really this question is just determine if the function is concave up or down and find the POIs. You're going to think, I'm going to do the same thing as what I was doing with the first derivative with my number line and examining the signs of the first derivative, except I'm going to do it with the second derivative. That's it. The same process as finding extrema, only with the second derivative. So let's take this function. I'm asking you to examine the concavity, whether we're concave up or concave down, where we have points of inflection. What should I do first? Find the second derivative, and what should I do with that second derivative? Set it equal to 0 so that we can find possible points of inflection. When f double prime is 0 or it's undefined, these are our possible points of inflection. I don't want you to call them critical points. They're kind of critical points for f double prime, but don't get confused with that terminology. If you see like a test question or a quiz question, if you're asked to find critical points, that's just with your first derivative. Instead, you're just going to try to find interesting f double prime points. We'll call them those. Okay, so we would take this second derivative, set it equal to 0, or see when it's undefined. Then we would analyze the signs of f double prime using those test points, just like we did with f prime. So first derivative, 4x cubed minus 12x squared. Find the second derivative, 12x squared minus 24x. Set this equal to 0. This will never be undefined, so I won't worry about it. We factor to solve. I get 0 and 2. These are my possible POIs, points of inflection. To determine if they are and to determine the intervals in concavity, I'll get my old handy-dandy number line out. And I'll analyze the signs of f double prime. So do that. I'll do it up on the board, check your answers, see if you got the same thing that I got. Cool. Any questions? Okay, well, let's go to what I consider the harder stuff, because if you understand how to do this for the first derivative, it's just one extra little step of taking one extra derivative, and it's the same thing. Only when you're seeing it's positive, instead of telling you if it's increasing or decreasing, now we know it's concave up or down. Okay? The trickier problems are the problems that come from the graphs of f prime. Okay? So just like I was asking you to find the extrema of f given a graph of f prime, I will ask you to tell me about the concavity of f given the graph of f prime. Okay, so sketch this graph. And the first question is, when is the graph of f concave up or concave down? Given that's the graph of f prime. Okay, well, don't copy this down. This is my thought process when I was dealing with extrema. I would look at the sine of f prime, and I would say, okay, at 0, we have a 0 derivative, so that's my critical value. I go from negative f prime values, and I remain at negative f prime values. So I'd say 0 is a critical point, but is neither a max or a min. You had something like that on your quiz today. Okay, you have a critical point, but not a max or a min. Well, now, instead of the sine of f prime, I need to analyze the sines of f double prime. On a number line. Okay? Because I know if I'm looking for concave up, f double prime is positive. Well, what do I have to look at on the graph of f prime to know the values of f double prime and to know if those values are positive or negative? Slope. The derivative of f prime gives me f double prime. Right? So the slopes of the tangents of f prime will give me the values, and it'll tell me if we have positive values or negative values of f double prime. So the sines of f double prime are actually the same as the slopes of the tangents of f prime. Not double prime, f prime. Okay? So, Mr. Ogletree, when is f, the graph of f, concave up, given this graph of f prime? Perfect. The slopes of f prime are positive when we are less than 0. Positive slopes, positive slopes, positive slopes, positive slopes. We don't even need all those pluses. We just can say they are all positive. To the right of 0, all of these slopes of the tangents of f prime are negative. So the values of f double prime to the right of 0 are negative. So f is concave up from negative infinity to 0. We are concave down from 0 to infinity. which means I have a point of inflection at 0. Tricky, right? It'll get trickier when I ask you, like, when is f decreasing and concave up? And I give you the graph of f prime. We'll worry about that next class. Here's another graph of f prime. Now that we understand the relationship between f prime and f double prime, and we can find the values, whether they're positive or negative, of f double prime, let's figure out when the graph of f, given this is f prime, is concave up or concave down, and let's figure out the inflection point of f. Check your answers with neighbors when you're done. Now, you can try to sketch the graph of f, but it's kind of tricky to sketch f correctly unless you already know the concavity of f. So it's actually easier to just go straight to finding the signs of f double prime, or finding the values of f double prime. Go ahead and check with your neighbors once you got it. I'm seeing a lot of people get it. Good. 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 How are we trying this, Mr. Meyer? Trying to sketch f and then find the concavity? F double prime? Beautiful. I like that. I see that. Yep. Positives, then a 0, then negatives. But we go from positives to a 0 to negatives, but then we come back to positives, right? So you need to come shoot back up. Ms. Gross, what'd you get? Where do we have points of inflection?
-2 and 1.
Perfect. -2 and 1 are points of inflection because to the left, what is the sign of f double prime, Ms. Gross, of -2? Positive, yep. We are concave up because the tangent slopes are all positive. You can either sketch the tangent slopes and see that they're positive, or you're like, hey, these are positives. Then we see we have a 0 tangent slope at -2. Then we have tangent slopes that are negative. Then we see we have a 0 tangent slope, so a possible point of inflection, which definitely is a point of inflection because the tangent slopes are positive to the right of 1. So we have inflection points at -2 and 1, And here's our concavity. We are concave down from -2 and 1, and we are concave up everywhere else. Yes, Mr. Wenzel.
So would it not be a point of inflection if it kept going down after 1?
Exactly. Okay. You can have situations where we don't change concavity. So let's think about concave up decreasing, concave up decreasing. I mean, it wouldn't have a nice derivative there, but this is a possible graph. I mean, it'd be an undefined derivative. It'd be a sharp point. I could have situations where we go concave up decreasing and then concave down increasing, something like that. Like this isn't pretty, but this could be a function. Okay, so possible situations. Okay, let's do one more. And then on the video, I'm going to provide more examples of functions and doing the second derivative kind of process to test. What do we think, Ms. Pennington? Yes. Don't say the slopes are decreasing. Say the slopes are negative the entire time, because telling us the slopes decreasing, you're talking about the second derivative of this first derivative. So they're all negative. So what does that mean? Exactly. The entire graph of f is concave down everywhere. Okay. We'd actually have a kind of a undefined situation where we have a possible point of inflection, but it wouldn't be a point of inflection. Okay. So there's no points of inflection. Now, let's talk and discuss, because you'll see it on your homework, something called the second derivative test. Okay? At a critical point, which is when f prime is equal to 0, or it's undefined, we can examine the second derivative to see if the critical point is a max or a min. Okay? So, let's think about that. If I have a critical point, say I'm looking at f prime, and at 3, f prime is 0. But say I don't know the signs of f prime to the left and to the right of 3. However, say I'm told f double prime of 3 is positive. Is f of 3 a max or a min? Max or a min? What do we think? What is f double prime being positive? What is that telling me? F double prime being greater than 0 is telling me I'm concave up at this point. If I am concave up at a critical point, is it a max or a min? A min. Concave up. This is a critical point where the horizontal tangent is 0. This is another way we can examine if we have extrema. I don't like using this way. It's confusing, actually, because you think first derivatives deal with maxes and mins, increasing and decreasing. Second derivatives deal with concavity, concave up, concave down. It's just an interesting thing that you can see, and there's actually a couple problems on the AP exam that I've seen over the years where you have to understand concavity to find maxes and mins. On your homework, I don't want you to use the second derivative test if you're asked to. You can use the first derivative test like you did last class, okay? I'll do more problems for the video. All right, let's do a couple more functions and examining the concavity. So all we need to do is take the second derivative, set it equal to 0, or see when it's undefined, then examine the signs of the second derivative, and we will figure out the concavity of this function f. So our first derivative, f prime is 0, so 0g minus g prime times f all over g squared. Since this is my first derivative and I need to find my second derivative, I will simplify this. Make sure it looks nice. And now I find my second derivative. I get f prime g minus g prime f all over g squared. This is supposed to be squared. Oops, let's go back. So this is negative 12x over x squared plus 3 squared. This will be fun. Here we go. The second derivative is f prime g minus g prime, which is 2x squared plus 3 to the first times 2x times f all over g squared. That'd be to the fourth. Well, actually, this isn't that bad. I see right away I can cancel one of these x squared plus 3's. Okay? So I can get a second derivative that is not that nasty. And we'll set it equal to 0, or we'll see when it's undefined. However, notice we have x squared plus 3. That will never be 0. So I just have to set my numerator equal to 0. So I have negative 12 times x squared plus 3 minus the quantity of 2 times 2x minus 12x times negative 12x. So that's negative 12x squared plus negative 36 plus 24/48 x squared. That's equal to 0. So that's 36. Let's just move down a little bit. Let's get rid of that guy. That would be really nasty. So this would be 36x squared minus 36 is equal to 0. So I can factor out a 36. I get x squared minus 1 equals 0. So I get x is equal to plus or minus 1. Not bad. Now, let's remember that my denominator is this. So really, this is my numerator, and my denominator is the x squared plus 3 cubed in my second derivative. So I have my possible points of inflection. I will plot them on a number line to examine the signs of f double prime. Here's -1, here's 1. I'll then plug in test points to see what the signs of f double prime will be. So let's take a value like 2. 2 squared times 36 will be bigger than 36, so this will be positive. 2 squared plus 3 cubed, that'll be positive. Positive over positive, this is a positive. I'll take something like 0. I get a negative on the top. I'll remain positive on the bottom. So that's a negative. I'll take something like -3. I'll be squaring it, then multiplying by 36. That'll make the top a positive. A -3 squared would be a positive, plus 3 cubed would be a positive. So here we see where the graph of f, my original function, 6 over x squared plus 3, is concave up from -infinity to 1. It is concave down between -1 and 1. It is concave up when x is greater than 1. And these are our points of inflection when x is -1 and when x is 1. You can go ahead and plug those values back into your original function if you want to see the location, the xy location of those. And we can go ahead and just check, and it's good when you're doing these questions to graph the original function and make sure that what you discovered is actually correct. So I'm looking for a point of inflection at 1 and -1. So at 1, it looks like we're going from something that's concave up to something that's concave down, and then back to something that's concave up. I can kind of zoom in, set my window to see that. Maybe let's go from -5 to 5, and let's go from 0 to, let's go to 5. I think that'll fit things in there. There you go. There you go. Concave up. We hit a point of inflection at -1. This top piece is concave down, hit a point of inflection, and then we're concave up. So beautiful looking graph, and it confirms our answers. We could look at something like this. We're trying to find the concavity between 0 and 4 pi. That's ambitious, but let's see how it goes. So take the first derivative. We get negative sine x minus 1. But we're going straight to the second derivative for concavity. So that is negative cos x is equal to 0. We know cosine is equal to 0 at all the pi over 2's. Let's just go to 2 pi here. This is a little crazy. Okay, so I will plot the pi over 2's. I will test points. Great thing about test points with trig functions is you can usually use some extremes. So an extreme test point would be like 0. Extreme test point here would be like pi. Extreme test point here would be like 2 pi. So I plug in 2 pi. Cosine of 2 pi is 1. It would be -1, so this is negative. Cosine of pi is negative. Take the opposite of it. That becomes positive. Cosine of 0, that's 1. Take the opposite of it, it's negative. Here are my points of inflection. And here is the concavity. Concave down, concave up, concave down. All right. Final problem, find the relative extrema and the inflection points of the function. Well, we kind of mentioned the second derivative test to find the relative extrema. I don't want you to necessarily worry about this. I want you to do what we did last class. I want you to find the first derivative, use the first derivative test to find the relative extrema. And then I want you to use the second derivative to find your inflection points. So let's do it. It's kind of like an intro to next class when we're kind of putting all things together. We'll take the first derivative, negative 15x to the fourth plus 15x squared. Set it equal to 0. I'll factor out a negative 15x squared. That'll give me an x squared minus a 1. This will give me points, critical points at 0, 1, and -1. So let's plot those. And hopefully we'll be able to find our extrema. So I Take a value bigger than 1, like 5. This will be positive. This would be negative. Take a value like 0.5. This would be negative. This would always be negative, so it'd be a negative times a negative. That's a positive. Take a value like negative 0.5. So this would be negative as well. This would be negative. This would actually be a positive. And then we take a value like negative 5. This would end up being positive. This would stay negative. So this would be negative. So we only have 2 extrema. We'll have a minimum at negative 1. We'll have a maximum at 1. This is when my function is decreasing. This is when my function would be increasing. And then we'd have, of course, 0, so we'd be constant at these locations. So that's step 1. That's the relative extrema. Find the inflection points. Let's take the second derivative. I'm actually going to go off of this unsimplified first derivative to take my second derivative. 15 times 4 is 60, so I got negative 60x cubed. 15 times 2 is 30, so I got 30x. I will factor out a negative 30x. I also get x, I'll get 2x squared plus negative 1 equals 0. So that's interesting. I get 0 as one of my inflection points, and then I'd get plus or minus root 1 over 2. That's because I'm setting this equal to 0. I get 2x squared equals 1. X squared is equal to 1/2. X is equal to plus or minus 1 over 2. So I would do another number line with my second derivative. I'm looking at 0. I'm looking at this 1 over root 2. That's negative, and a positive 1 over root 2. Might be interesting to test these points. Maybe we're going to think about values just a little bit positive, a little bit negative. Let's just start with a big positive value like 10. This would be positive. This would be negative when I plug in 10. So that would be a negative, so we're concave down there. Now let's think about a value very, very small but positive. Very, very small value squared times 2 would be still very, very small and positive. Add a negative 1, that'd make it a negative. Negative 30 times a very, very small positive value, that'd be negative. So we're talking about a negative times a negative, that'd be positive. Then we go to the other side. Same thing would happen here. We would be, oh, this is interesting. So I plug in a very small negative value, square it, multiply by 2. It's something very small and positive. Add 1, that's a negative. However, here, it'd be a negative times a negative. That'd be a positive. So this would be a positive times a negative, which is a negative. And then I look at negative 10. A negative times a negative is a positive. This would be a positive value because you're taking your negative value squared. So positive times a positive, positive. So very interesting. We are concave up from negative infinity to negative 1 over root 2 for my function here 2. And these would be our points of inflection. Here, here, and here. And if I graph this, I'm going to do this just for fun. I would like to see those results. So I have negative 3x to the 5th plus 5x cubed. You, of course, won't have the luxury of checking your answers with the calculator on your quizzes. I'll zoom standard just to see everything. So we are decreasing until negative 1. Good. We are increasing. Let's zoom in on that. Decreasing until negative 1. Good. We are increasing until 0. Then we neither have a max nor a min, but we have a horizontal tangent. We're increasing past that until 1, and then we're decreasing past there. So this checks out. And then I look at my concavity. I'm concave up until I get to this negative 1 over root 2, which I'm guessing is going to be right around here. And then I'm concave down, and then I'm concave up until positive 1 over root 2. That looks good. And then I'm concave down. So hoorah, fun problem, concavity maxes and mins. All right, that's it. Do your homework.